Massachusetts Institute of Technology, and he's going to talk to us about reducibility and computational lower bounds for problems with finite sparse structure. Thanks very much, Gavin.
Thank you. So thanks for the invitation to speak here. This is joint work with my student, Matt, and Wasim, who's a postdoc at MIT. So this talk is in part about computational lower bounds, but even more so, it's about understanding connections between problems. And so my main hope that what you take away from this talk is the motivation to understand relationships between statistical problems. Okay, so I'm going to spend probably significantly too much time setting things up and motivating, but I think it's important for those of you who don't work exactly in this field. And so, yeah, so quite a bit of time motivating things, but I'll try to go as fast as possible, and then I'll get to the technical contributions. So, all right, so for me, this whole involvement in this area started with the spiked covariance model, the model for sparse PCA. So I'll just, 5 seconds give you the overview. So you observe samples in the detection or hypothesis testing variant. You get n samples that are in the null hypothesis, just isotropic Gaussian in d dimensions. An alternative hypothesis, the covariance has some rank 1 spike, and that rank 1 vector is sparse. So it's k-sparse. This means that it's a unit vector with k non-zero entries. All right, now you're supposed to detect between either of these. In all of today, the notion of solving a statistics problem is going to mean that the type 1 plus type 2 error is going asymptotically to 0. So just consistency, and I'll say it's possible or solvable, variants of these words. That just means for a given set of parameters, you can have this going to 0. Now, this is the prototypical high-dimensional stats problem in many senses. It has a whole bunch of parameters. That's really all you need to be a high-dimensional stats problem. So there's dimension, sparsity, number of samples, signal strength. And I'll talk about a little bit about this problem and about other problems that also have a bunch of parameters. So history of statistics, 25 years of statistics at least, in 20 seconds, from my view, it goes like this. So in the 90s and 2000s, people started looking at these high-dimensional problems, and they said, oh, gee, these are underdetermined. You can't get a consistent estimator unless you have some structure on your signal. If there's sparsity or low rank or all sorts of other structures, then you can do something statistically. Somewhat later, just in the last 5 to 10 years, there was a different realization, and to the best of my knowledge, the first time this was observed in a statistics problem, a natural statistics problem, was by Quentin and Philippe here in the audience. And what they observed is that while the threshold on the signal strength theta for the spiked covariance model is given by one number, there's actually a different threshold for computationally efficient algorithms that's given by a very different number. And when I saw this was kind of mind-blowing. It's like, wow, this isn't the number we should be caring about. This is the one that's much bigger, if you care about computationally efficient algorithms, and presumably everybody here does, because at the end of the day, you're going to try to run it on some computer. Okay, now I'll get into details about what computationally efficient means, what lower bounds mean, and so forth. So their paper concerns not exactly this model, the spiked covariance model with Gaussian distributed samples, but a somewhat different one that I won't get into, which has the same flavor. Chao Gao and Songming Ma and Harry Zhu showed that the exact same thresholds hold for the Gaussian spiked covariance model. So sort of slightly more stringent set of distributional assumptions. Okay, so like I said, this result really changed the way that I thought about statistical problems. And there was one intriguing question that I couldn't understand completely. And what that was what about sort of how does this look like for different values of the parameters? And it turns out if you dig in these papers that these papers show tight hardness for a single scaling in the parameter space, meaning n is scaling proportional to d, k is roughly root n, and the signal strength is then constant because the computational threshold was k squared over n. And so, I was just kind of new to this, and I thought, let me try to understand, can we get a more complete picture of the hardness for sparse PCA with the Gaussian distribution? So this is how I started thinking about this, and we'll see that it led to some other things as well. All right, so why should we hope for a more complete picture? What does a more complete picture even look like? What are we shooting for? So there's a different paper of Zhongming and Yihang. They called it large average submatrix. It's also called biclustering, and this is the problem. And for this problem, they got what you easily think of as sort of a very complete picture of the hardness. So here's the problem in a nutshell. You have Gaussian variables in a matrix, standard Gaussian. An alternative hypothesis, there is some submatrix, k by k. They don't have to be adjacent, obviously, just some collection of rows and columns where the Gaussian variables have elevated mean, where that elevated mean is denoted by lambda. Now they drew this wonderful diagram, and they said, look, if you let k scale polynomially in n with some exponent alpha, you let lambda decay polynomially in n with an exponent beta, one gets this sort of diagram that partitions the space of parameters into three regions, impossible, hard, and easy. One thing that's worth emphasizing before I say what these regions mean is just that this whole diagram and every diagram I'm going to talk about is up to polynomial factors. So if there is sort of, when you jump from here to here, you're changing alpha by a constant, and so you wouldn't see, for instance, polylog terms and so forth, polylog factors. Okay, so impossible means information theoretically impossible. You just can't do it. There's not enough data. Signal strength's not high enough. Hard means computationally hard, subject to finite clique hypothesis. It'll say what that is. Subject to a complexity theoretic conjecture. And then easy, easy just means easy. I don't even need to say anything about easy. It just means there is a simple, efficient estimator that works here that has type 1 and type 2 errors going to 0. Okay. There's actually another problem for which there's such a complete diagram. And this was done by Hayek, Wu, and Xu. So this is a community detection problem. You have one community, denoted by nodes in green. They have some edge connection probability that's somewhat higher than the edges outside of the community. Obviously, as a statistician, you don't see the colors, and your question is, can you find the community, or can you even detect that it's there? Now, this problem on the surface looks almost the same as the previous one, except for now you have Bernoulli variables. So Bernoulli Q outside the community and Bernoulli P inside, and you're supposed to detect if P is not equal to Q, or if there even is such a community. And I just want to emphasize that because this is actually a graph and you have symmetry, and so the diagonal also doesn't mean anything in a graph, these problems turn out to be significantly different technically. And we go also in our paper into a lot of technical work to deal with the fact that this is a graph and not a matrix. But I won't say anything else about that in the whole rest of the talk. So I'll just draw things as matrices and describe things in terms of matrices. All right, so again, they have actually the same diagram for this Bernoulli case, which looks like the same problem. It's just Bernoulli, and it's the same diagram. Okay. So how does one show computational hardness? If we claim that this is hard, what does that mean? Before I go there, I'll just mention that their result assumes that there is some constant relating the in-community edge probability to the out-community edge probability. Let's say 2 or 3 or 1. One of the questions that we're motivated by is, what about other scalings of P and Q? Right, it's one of the questions left open by this paper. Okay, so how to show computational hardness? Let's see. So the way this is done is by showing reductions from hard problems. And if you go back to the beginning of complexity theory, Karp has sort of arguably the foundational paper for the whole field of NP completeness, even though he wasn't the one who showed NP completeness. That was Cook and Levin. But what he showed is that this notion of reduction from one problem to another. So for instance, you might have a stat formula. You want to show that some other problem, let's say independent set in a graph, is hard. You know that stat's hard, right? Boolean satisfaction. So what you do is you produce an instance of the graph, and for any instance of the stat formula, you produce a graph. What then one concludes is that if you could solve the graph problem, you could then solve stat. And so if stat's impossible to solve, the graph problem must be impossible to solve. And so one thing that's noteworthy for us is that this whole setting is worst case. That's what's traditionally done in complexity theory. And the way that comes about, that it's worst case, is if you take a stat formula, and for instance, you want to reduce to independent set, then each variable goes into a graph with 7 nodes, and there's certain specific subgraphs depending on what's going on in the clause. So each clause goes to a graph in 7 nodes. And in particular, you don't get a graph that's any reasonable, sampled from any reasonable distribution over graphs if you started with a reasonable distribution on SAT. Let's say uniform over over formulas, you map to graphs. You get some weird distribution on graphs. So these mappings are inherently worst case in nature. They say you can solve any graph, any independent set problem, let's say, then you can solve any SAT problem. They don't tell you what you can do in the average case setting, which is of interest to us. I mean, all these problems that we're interested in studying have a probability distribution describing your data. All right, and of course there is a whole theory of average case complexity in the CS theory literature. Levin's, it's somewhat different. I won't get into the details, but happy to chat about it. All right, so Karp produced this beautiful figure in his paper. He said, here's satisfiability, and one can map to all these different problems and use various problems as intermediates and understand relationships between combinatorial problems. And as everybody here knows, this has had just a big effect on how people think about algorithms and complexity. Okay. So the dream might be to try to produce a similar sort of diagram for statistics problems, at least of a certain flavor. In order to elucidate relationships between problems, get sharp hardness diagrams like the ones we saw, and do all of this in an average case reduction sense, right? And so I'll say that this is quite premature to know whether this sort of program is going to yield any real fruit, but yeah, it's our sort of first tiny step in hopefully that general direction. Okay, so the first question is, what's the appropriate notion of reduction? If we don't want worst case, what's average case reductions look like? So actually, reductions are not something new to statistics. LeCam has a notion of reduction that is very useful and in this context, and it just had a significant impact on statistics. And the idea is that you have two statistical experiments, E and F, and each of these is a collection of probability distributions described by the same set of parameters. In this talk, because we're doing hypothesis testing, the set of parameters is just binary. Introduce this notion of deficiency. So this is the infimum over Markov kernels K that are going to map a distribution P to something that's close to distribution Q. One then takes worst case over the parameters and then looks at the total variation between these two. And the way to think of this is that P is transformed by the Markov kernel into Q. If you can solve Q, well, then you can solve P because you can transform P into something that looks like Q and then use whatever algorithm you have for Q. Put another way, any estimator for the F family, there exists an estimator for the E family that has risk that's at most delta bigger. And that tells you, as a corollary, of course, that the minimax risks are related in this way. And so we would think of this sort of relationship as saying that Q is at least as hard as P. So it's sort of a partial order on these problems. All right, so that's LeCam deficiency. What Philippe and Quentin did is they added the word computational everywhere. And this does wonderful things. So you can think of computational deficiency between two problems, and now we restrict the Markov kernel that maps one problem to another to be polynomial time computable. So efficiently computable. And then if there is an efficient algorithm to solve the F problem, then there is an efficient algorithm to solve the E problem, just by exactly the same argument as before. Because end to end, your algorithm that composes K and your estimator for F is going to yield an efficient algorithm for E. Okay, so this is the notion of reduction, this sort of a statistical notion of reduction that was put forth in this paper, and turns out to be very suitable for statistics problems. Okay, so that's the notion of reduction. The other question you might wonder is, what's at the root? Satisfiability is at the root of Karp's tree diagram. So what's at the root here? And again, from Quentin and Philippe's paper, plan and clique, as I mentioned, is at the root. So what is plan and clique? So plan and clique is another problem that looks very similar to the ones that I've described so far. One has an n-node graph, which I'll draw as a matrix, and then null hypothesis. One has an error-distributed random graph with, let's say, edge probability half. An alternative hypothesis somebody has placed a clique somewhere uniformly at random, and we're specifically going to assume that it's uniformly located so that the alternative hypothesis is just a single probability distribution. It's not a composite hypothesis testing problem. This is simple versus simple. And I won't go into it, but that actually turns out that most of the reductions that we do are simple versus simple, and that helps us for various technical reasons. Okay, so this is Planck clique. There is a clique there of size k, or there isn't, and your goal is to determine if there is or isn't. You can convince yourself pretty quickly. Yes, please.
That's a uniformly located clique of size k is a simple hypothesis?
It's a mixture of overall subsets of k nodes, and you put a clique there.
Sure, okay.
Yeah, so it's a uniform mixture of all the probability distributions, yeah. Okay. All right, so if k is bigger than 2 log n, you can find it because every strand in your random graph has the biggest clique of size 2 log n. Okay, this one sticks out. If k is bigger than square root of n, then you can find it efficiently. When k is 2 log n, and you can find it just by searching, but that's obviously not efficient. That is time n to the log n, so quasi-poly, but not poly. K is bigger than root n, then a lone Kuryelevich-Sudakov showed that a spectral algorithm can solve the problem. And there have been various other sort of algorithms and contributions in this direction, but no algorithm that anybody has found can beat this root n, and so it's conjectured to be computationally hard. And there has been sort of a rich line of work to understand in what way and why, and trying to really convince ourselves that indeed that's the case, that this problem is computationally hard when k is less than root n. And formally stated, you can call this the Planck clique hypothesis. This says if there's any sequence of polytime algorithms A, k is scaling like n to the something less than half. G is coming from the Planck clique problem, which means that under null hypothesis it's arbitrarily half, and alternative hypothesis there's a clique planet. Then the asymptotic type 1 plus type 2 errors is at least 1. Right? And so this is the hypothesis. It's saying you can't do anything reasonable in this problem. Okay. So what are the implications of assuming this is hard and then in turn finding a reduction? Well, the way that we're going to draw these pictures is Planck clique is just this funny little one-dimensional diagram. There's the first half from 0 to half in the polynomial scale. This problem is hard because k is less than root n. Of course, there's something when k is exactly half, but I don't really care about that fine of a granularity. And then there's a sharp threshold. As soon as one crosses, as we know, this problem becomes easy. So this is the diagram, and if you want to show that something's hard in your problem of interest, then the way to do that is to map some point on the hardness diagram here to the hardness diagram here. And your mapping had better be polynomial time, as we discussed. All right, so just to be a little pedantic, what's actually happening is that you are mapping a pair of distributions to a pair of distributions. Here's our Markov kernel. And the requirement that comes from the LeChem deficiency is that the total variation between the mapped distribution and the distribution of interest is going to 0 under both H0 and H1. So we want the LeChem deficiency to go to 0 so that if you can solve one problem, that tells you can solve the other one. Consistency in one implies consistency in the other. Okay, so this is the setup. What's the current state of affairs? Well, there have been a number of very nice papers showing average case reductions for statistics problems. All of these are from Planck clique. The Sparse PCA, RIP certification, biclustering or large average submatrix, Planck dense subgraph. But this isn't that many problems in the grand scheme of statistics problems, so where are the other problems? And a relevant quote is from Oded Goldreich. He's a very famous complexity theorist. And he gave this quote in a slightly different context in sort of just average case complexity broadly. And this whole problem of mapping one distribution to another appears to be challenging. And that's what he pointed out. We seem to be lacking techniques to do these sort of reductions, to reason about the complexity of average case problems. So because of that, the complexity theory community is focused on hardness for specific computational models, in particular sum of squares, Charlie Adams, and other hierarchies, as well as what's known as the statistical query model. And these restrict the computational power of a specific sort of, you could think of a specific computer has some limited computation that's encoded in this way. And so these are unconditional lower bounds, whereas these are conditional on Planck clique being hard. Okay, and there's a line of work in this direction. All right, so back to slide 2. The hope was to understand, just build a little bit on the prior work on sparse PCA hardness and just flesh out this diagram a little bit. So we thought about this for a while. In the process, we came up with a number of techniques to map through other problems as intermediates and understand somewhat better picture for sparse PCA. It's currently only tight for k is bigger than root n, so it's sort of for half of the phase diagram, but we don't know the answer at the moment for the other half, although we have work in progress that hopefully will finish soon that does answer it. So anyhow, so here are a few techniques that I described, and once we developed these, we sort of got a little more intuition for how to come up with these techniques, and we were able to map to a number of other problems as well and understand relationships between these problems. So, so this is sort of the outline of the whole talk, now that I'm exactly halfway through the whole talk. This is the outline for what's left. I'll tell you about some of these techniques, and I'll sort of describe the theorem a bit that describes this picture. Before I do that, though, I want to address a couple questions that information theorists tend to have about this, and sometimes statisticians. So one question is, well, this is great, but what if plan and clique turns out to be easy? Then everything you've done is garbage, right? I hope not, and the reason is that relationships between problems are still hold, regardless of whether plan and clique is easy or not. So if you come to me and you can solve this problem that we made up called planet stochastic block model, then that tells you immediately that you can solve various other problems. And that's one way to put it. The other way to put it is that it significantly raises the stakes. So not only is it pretty awesome if you can solve sparse PCA in a previously conjectured hard region, but now you've solved a bunch of other problems as well. So that's one. That's one way to address that question. The other way to address that question is all this stuff, like up to polynomials, and people know that SAT is solved every day on, even though it's NP hard and all this stuff. So, like, maybe there's a constant that's 10 to the 10 to the 10 to the 10 in front of your polynomials, and so none of this stuff is relevant to the way algorithms actually run. But my answer to that is that all of the reductions here are super efficient, quadratic or linear or something. And so if you find an algorithm that in practice runs on one of these problems, then you've genuinely solved plan and clique in practice, which hasn't been done. There have been cryptosystems built on plan and clique. So that would be a shock to everybody also from the empirical direction. And who cares about the arbitrary polynomial that may or may not be hidden? All right. So with that, quick recap of our goal. First is to have a little web of average case reductions between problems. Second, like I said, is to give a few new techniques for average case reductions, for mappings between statistical problems. And as a byproduct, to get the full hardness diagram for a number of problems of interest. I said we made up this planet stochastic block model that was in the corner there. Most of these we didn't make up. Most of these are problems that people have studied before and are interested in. Okay. Like I said, sparse PCA picture is only complete for k is bigger than root n. And actually, our planet dense subgraph picture, we do get for general P and Q, subject to a condition that the distance between P and Q is no more than the rate of sort of getting closer to one another. So if the difference between them is scaling polynomially n minus gamma, then gamma has to be bigger than n minus alpha, which is the rate of decay. So in some sense, there's half of the parameter space here that we also didn't address. And this turns out to be something called the log density model studied by Charikar and co-authors and various others. And it seems to have genuinely different behavior. So I'm not sure if there's hope to get a reduction or not. Okay, so here's the theorem. Not unfortunately described here in terms of equations. You're welcome to go look at the paper. But here are the pictures that are produced that are analogous to the previous pictures I showed. So each of these pictures has hard, easy, impossible. For two different problems, the detection versions that I said, the hypothesis test between H0 and H1, as well as the recovery or search variants of all of these problems, which are not based on planted clique, at least not for all of them. For some of them, the search version is based on a conjecture for planted dense subgraph recovery at a particular scaling that was done by Chen and Xu. And that gives rise to the pictures for recovery, which are superimposed on the pictures for detection, which is why these diagrams, some of them, like this one, has a whole bunch of regions. It's because there's a gap between what's detectable and what's recoverable. Okay, so we go into the recovery story somewhat in the paper. We get some intuition for when is there such a gap between recovery and detection? When do they not appear to be the same? Well, in other problems, they are the same, like this one's rank 1 submatrix that I'll describe. Why is there a gap? Sometimes why is there not a gap? Other times, we talk about that in the paper, and I won't talk about that in the next 20 minutes. What I will talk about is some of the techniques, not all of them, but some of them that are here, that give rise to this diagram. Yeah, so I'll get through as many of these as I can. I probably won't get to random rotations, which is how one maps to sparse PCA. I'll skip over planted clique lifting and some of the technical ideas that are really crucial, which are to sort of do things not in one shot, but to do things in many, many steps and to bound the total variation in each step sequentially. And that's something that appears throughout, but I won't talk about that. It's sort of technical in nature. And what I will talk about, the first idea is rejection kernels, and that just builds on ideas from a previous paper, but it turns out to be very important here. So I'll start with that, and then we'll go into these notion of graph lifts. There's no notion of graph lift using Poisson variables, notion of graph lift using Gaussian. The idea here is to use distributional properties of these random variables, in particular the fact that they're infinitely divisible. Then there's this really strange technique that gives the sharp hardness for rank 1 submatrix, and I'm really going to dwell on this one hopefully as much as I can, because I think in some ways this is the technique I think that's coolest. Yeah, and then I'll conclude. Okay, so rejection kernels. The idea behind a rejection kernel is to change the distribution from Bernoulli, you start with planted clique, to a different probability distribution. And this was done by Ma and Wu, and as well as Hayek, Wu, and Xu. And the reason why is because here they have a Gaussian problem, and one wants to map here from planted clique. So how does one get Gaussians out of Bernoullis? So in this part of the hardness diagram, when lambda is on the order of constant and k is between 0 and half, sorry, k is between log n and square root n, alpha is between 0 and half, one can just do mappings that are entry-wise. So one starts with your planted clique matrix, does an entry-wise map, and gets a Gaussian. And I'll describe that entry-wise map. And that should be intuitively natural because k here is exactly in the region where planted clique is hard. Lambda is a constant, and there's sort of a constant difference between Bernoulli 1 and Bernoulli half. So it makes sense that these should be relatable. So how does one map Bernoulli to Gaussian? Well, what you want, you simultaneously have to map Bernoulli half to standard Gaussian and Bernoulli 1 to the elevated mean one. So what you want, it turns out, is that you want a mapping phi that takes 1 to p, and you have to do that because 1 is to go to p here. I denoted elevated mean 1 by p. You also want that 0 maps to 2q minus p, distributed random variable, where these are the densities. And why do you want that? Well, then obviously phi of Bernoulli 1 is just always just phi of 1 is drawn from p. Phi of Bernoulli half is then the mixture, which is q. Now there's a problem with doing this, which is that 2q minus p might not be a probability distribution. It, in fact, will never be a probability distribution. Here's an example. If we had q and p as elevated mean by 0.4, then 2q minus p gets negative, and so in Ma-Wu, what they did is they just truncated the distribution and hoped that it was close, and indeed they showed that it was close. One didn't induce a big loss in total variation by truncating the distribution. So one maps to 2q minus p is subject to this conditioning on the positive, being in the positive part of the line. All right, so we slightly generalized this idea to map, instead of from Bernoulli 1, Bernoulli half to Gaussian, map to arbitrary densities f and q from which one can draw samples. And the arguments are not terribly complicated, but I won't go into a lot of detail. But the idea is that you're hoping that you can sample phi of 1 from some linear combination of the densities f and g with these weights, phi of 0 from a different linear combination. Because of non-negativity, you can only sample on this set where these functions are positive and they turn out to be correctly normalized. And the name that we used for this general procedure is a rejection kernel because it's based on rejection sampling. And really, the way to think of this is that it's a slick way of subtracting PDFs. Here you have to subtract PDF, G and F. It's a slick way of doing that using only sampling black boxes for F and G. So you don't actually need to have functional forms for F and G. All you need is a black box that produces samples. You do some rejection tricks, and one gets something that's actually not exactly from what you want, but close enough in total variation. So okay, so we can map to other distributions than Gaussian, and that'll be useful. So, but first, let me just say a few more words about Gaussian. So here's the Gaussian problem. We said that by these maps, you can get to the hardness on the bottom here. Actually, the interesting part, the most interesting part at least, of this paper is this little angled part of this triangle. Why? Because it's saying that there's a trade-off between the size of the submatrix that you've planted there and the signal-to-noise ratio. So I think that that's really fundamentally what makes this different from planted clique. Right? It's not just a single parameter k. The SNR plays a crucial role. And how did Ma and Wu capture this trade-off? So they actually have an internal reduction within this problem. One starts with assuming this is hard, and one maps to somewhere along this line. This line turns out to be lambda k squared over n is constant. And what they did in their paper is they sort of averaged over blocks. We can check that averaging over a 2x2 block moves us in the correct direction. So all that's done here is you just add up all the entries in sort of every 2x2 block. You divide by 2, not by 4, because you want the variance to be still 1. K is going to stay roughly the same with high probability. Each of these entries lands in a different block. N got smaller by a factor 2, and the elevated mean got smaller by a factor 2 when we normalized by 2. And one can check that this moves us along the correct trajectory on that line. So I think this is conceptually, to me, the coolest part of this whole diagram. Of course, the technical elements in this paper were fairly significant to deal with various issues. We're going to do the same thing in a different way. It turns out to be necessary for dealing with graphs, and it'll generalize in various other directions. And here's what we do. So we're going to move along the same trajectory along the triangle. We're going to use orthogonal invariance of the Gaussian distribution to take a single Gaussian random variable into two Gaussian random variables. Philippe calls this cloning, and he's the one who showed me this in the context of statistics problems. But thanks, Philippe. But anyway, if one adds an independent standard Gaussian to x, which has this elevated mean, and subtracts the Gaussian from x and normalizes appropriately, you suddenly have two Gaussians. And like I said, this is just orthogonal invariance of Gaussian distribution. So if these are independent, this is an orthogonal matrix, they remain independent. And what one does with that is one can blow up each entry here into 4 entries. And this does something completely different to your problem in terms of the parameters. Now k got into 2k, n is 2n, and lambda again got divided by 2, and one can check that magically enough this actually moves us along the exact same trajectory. So here's an alternative way to capture this hardness triangle. All right, so back to graphs. If you care about planet dense subgraph, then what you could do is you could start with planet clique, you map to Gaussians, you do this Gaussian lifting procedure to change the parameters to move along the triangle, and then you can just threshold to get back to graphs. You get q that's half. If you threshold the standard Gaussian, you get p that's half plus constant order and lambda. And this gets tight hardness for a specific regime of PDS that's scaling like something here, half and half plus n to the minus alpha. that's one specific scaling of planar dense subgraph. What about the general scaling? So here the idea is to use not the Gaussian distribution, but Poisson distribution. Poisson has different behavior than Gaussian, so it'll be useful. So here one starts with planar dense subgraph that we just got using the Gaussians and thresholding. So we have Bernoulli Q and Bernoulli P, where Q is this and P is a little bit bigger. Lambda here you should think of as n to the minus beta, so it's decaying. Using the exact distributional map that I presented a few slides ago, you can map to Poisson random variables with different parameters, constant times Q and constant times P. One can use the beautiful property of Poisson distributions, the Poisson splitting property. You can magically turn one Poisson variable into 4. Turn each entry here into a 2x2 matrix, and do this log n times. You get some new set of parameters. Who knows what this has done for us? You threshold the Poissons at 1 and bigger and 0, and one gets something that's close in total variation, or both hypotheses, to this sort of general scaling of planar dense subgraph that I claimed before. So the high-level idea is just go to Poisson. Don't try to do this in the graph world of Bernoulli's. You can do the manipulations that you like without any loss in total variation. When you're in the Poisson world, because Poisson has these nice properties, and you pay the total variation cost up front when you're mapping between Bernoulli and Poisson, and finally at the end when you go back, and you can control those total variation errors.
Wait, the map from Bernoulli to Poisson lossless?
No, you pay, yeah. There's, yeah, thanks, yeah. Yeah, all of these rejection kernels induce a loss when you map from Bernoulli to the other pair of distributions. Okay, cool. So there's time for flexion cloning, which I'm super happy about. That's the main thing I wanted to get to. And so the problem that this is useful for is rank 1 submatrix, which turns out to be, it's essentially the same as Sparse Spiked Wigner. And apologies here and throughout the whole talk for the undoubtedly many references that I missed. Please let me know if we've also missed them in the paper. Yeah, so what is Sparse Spiked Wigner? Well, it looks a lot like the covariance matrix of Sparse PCA. You just have a symmetric Gaussian matrix with a sparse rank 1 spike. Rank 1 submatrix just doesn't have the symmetry constraint. So here you have a Gaussian matrix, and here you have lambda, k, v, u transpose. V and u transpose are unit vectors. So that's why we rescale up by k, because you could think of them being as like 1 over root k entries for each. So this is this model, and I want to understand the hardness diagram for it. Well, it turns out that it does not have the same hardness diagram as the seemingly very similar problem of biclustering, where this was Gaussian with elevated mean lambda. This has a completely different hardness diagram. It's not this one, it's this one. So the hard regime is sort of bigger. The slope of this line, in particular, the edge of the hardness region, is a different slope. So there's a different interaction between the size of the planted matrix, K, and the signal-to-noise ratio, lambda. So a puzzle that you'll see the answer to in 2 minutes, like, why is there a different scaling? Why is this problem so different than just the elevated mean large effort submatrix problem? So in order to understand that, we'll just observe that this line is described by lambda squared k squared over n being a constant. So we're going to try to keep this constant. The previous line, the previous sharp threshold, was described by lambda k squared over n. And so what this says is that you better not, if you're moving along here, you better not decrease lambda as much, right? Because you're paying now a square and you're decreasing of lambda. So we need to increase k without decreasing the signal as much. And what turns out to be the answer to this is to avoid adding noise. So remember before, when we did this Gaussian cloning, or Gaussian lifting, we started with a single Gaussian, x, we added z, and we subtracted z. Z was just some independent Gaussian that we sampled on our own that had nothing to do with the original problem, and now we got 2 samples, and then you iterated this. We're going to try to do the same sort of thing without adding in extra randomness, because that extra randomness is killing the signal to noise ratio. Okay. All right, so I'll just also say that the lower bounds are true already essentially for U and V just having half of their entries being plus 1 over root k and minus 1 over root k, in which case you get the submatrix that looks like this, minus lambda, 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 minus lambda. And in some high level, this is really important. This is the difference from the elevated mean case, because now you have negative entries here. So this is different. And we'll see that that's what gives us the flexibility to do the same thing without adding noise. Good. So, okay, so here's the technique. One starts with an instance of the Gaussian biclustering or Gaussian large average submatrix. There's this little block here, and we're going to assume it's entirely elevated mean at lambda. And we're sitting on this point. You start by copying the whole matrix. These two are just exactly the same. You flip this bottom one and multiply only the top half by minus 1. Now I'm schematically drawing the planted part as entirely being in the bottom just to make it easy to understand. The red now means it's negative, so it's minus lambda in this square. Now you scale down by root 2 just to get the variance to still be 1. You add them. In the top half of the matrix, you have the top minus the bottom, because this was flipped. It's the bottom, and there's a minus. The bottom here is top plus bottom over root 2. And so if we forget about the planted part, the blue and red, and you just think about the Gaussians, then everything, all the entries here are just independent Gaussians still, right? Because it's still an orthogonal transformation. You're adding 2 Gaussians, and the difference of 2 Gaussians are still independent Gaussians. So this is it. This is the procedure. Now you iterate this, so you repeat it horizontally with the horizontal flip or horizontal reflection. When we normalized by root 2, we lost a factor root 2 here. You lose it again when you repeat the thing again in the sort of up and side to side. And now what this does to the scalings is that lambda got smaller by a factor 2, k grew by a factor 2, and didn't change, and so we exactly moved along the correct trajectory, and therefore achieved this hardness diagram. Okay, so maybe one obvious thing to say, but it's a little late to say it, but sort of all you really need to do is show hardness for this bottom part, because going upwards just means adding noise or killing your SNR, which is sort of trivial to do. So yeah, so this achieves hardness along all these points down here, and completes the description of reflection cloning. Okay, so yeah, I guess I'll conclude. This is sort of the overview slide. I don't know if I mentioned it's on archive as of a few days ago and will appear in Colt in a couple of weeks. And I'm very, very happy to get any questions. Before I do that, I'll just end with one intriguing little question that seems to arise, which is that a whole bunch of algorithms appear to be optimal or nearly optimal for planted clique. Spectral, the natural SDP, just add up the whole matrix, add up the Rosen threshold, and so forth. But under the reductions in various of these problems, the same natural algorithms perform wildly differently from one another, which is somewhat weird that one starts with sort of all of these algorithms performing essentially the same up to polynomials for planted clique. All the hardness reductions are based on planted clique, and when one maps from there, one gets different algorithms that are optimal in different regimes. That's just a curiosity, I guess, and I'll end there. Thank you.
So, thank you for the talk. Good way to start the morning. So you spoke very briefly about restricted computational models, right? Or like Oracle models of computation or whatever you want to call them. Is there a notion of reductions that sort of preserves the computational model as well underlying things, or is that just...
That's a great question. It's something that we've started thinking about, but not that I know of. Yeah. For some of squares, it's delicate. You have to satisfy various properties for things. It becomes a little messy. I think for statistical query, it's probably not terribly hard to do, but yeah, it depends on the model of computation. That's a great question, though. Yeah. Yes, please.
Very interesting. So I have I think a much more unfair question.
That's
which
great.
is,
Yeah.
So suppose I really only cared about linear time algorithms or nearly linear time algorithms versus everything else. I imagine that's a very different question because, you know, the root has to be a different problem and all the reductions have to be linear time or nearly linear time. Is this, like, can you say anything about that?
I personally cannot say anything about that, but there is, and that's also something that we're starting to look into, but don't have any results on. So there's this whole area of complexity theory that's become very active in the last few years called fine-grained complexity. And there the idea is genuine, like quadratic lower bounds, for instance. So saying that you can't solve some problem in time n to the 2 minus epsilon for any epsilon. And so that's the sort of flavor of result that you're asking for. And there is even a recent paper that shows average case fine-grained hardness for some very weird problems that don't really make any sense. But one would like to do that for various statistics problems. Absolutely, yeah.
I do one more.
Maybe two more. Just do both, yeah.
So in the other model where the so for planted dense subgraph or the probabilities were a certain different power, you call this the log density model?
Exactly, yeah.
Do you have any idea so why these types of techniques don't work, or why it makes the problem very different?
Yeah, so in that setting, in Charkar's paper, they have a weird combinatorial algorithm that searches for essentially cliques of a certain size. It does do an exhaustive search over cliques up to a big constant size. And yeah, I mean, the setting of the scalings of the regions would just have a different appearance than they would here. But I will say that Passon, Menarangsi, and co-author have a very recent paper, I think from this Fox, I'm not sure, where they show the tight lower bound for that setting for Shirley atoms. So under that computational model. Yes, please. Yeah.
This is also possibly an unfair question, but this is also a min-max point of view. It's a computational min-max point of view, right? Because you're somehow, because the clique is uniformly planted, you're going back to your root. Now, suppose that you try to move, if you want, in the Bayesian direction some way, and say, well, you know, you are only interested in things where the planting is of entropy bigger than or equal to something.
Mm-hmm.
0. Any work of that type?
I don't know of any, and I haven't thought about that at all. But it's a good question. Yeah. Yeah. Well, I mean, one could imagine producing some sort of reduction that distorts that. I will say that Levin's average case complexity theory addresses arbitrary distributions over instances, and so maybe one could get something out of that framework. But unfortunately, that framework is very stringent, so that you can have the strength to reduce to arbitrary distributions in that way. And so the results in that whole direction are very limited. But it's a good question, yeah.
Thank Guy again for a very interesting talk.